This is one of the problems about blood. And it says, blood can carry excess energy from the interior to the surface of the body, where the energy is dispersed in a number of ways. While a body is exercising, 0.6 kilograms of blood flows to the surface of the body and releases 2000 joules of energy. The blood arriving at the surface has a temperature of the body interior 37.0 degrees Celsius. Assuming that blood has the same specific heat capacity as water, determine the temperature of the blood that leaves the surface and returns to the interior. One of the things to notice is the significant figures. Look at the 0.6 kilograms and then the 2000 joules, both only one significant figure. So at some point that's what we have to deal with, and then later on, when we calculate the temperature difference to only one significant figure, that's then what we have to subtract from the 37.0 degrees Celsius. So to begin with, I realized that they want from us the absolute temperature, but here with the specific heat capacity, we're calculating a delta T first. So that's the question mark here, and then later on we're going to subtract that from the 37.0 degrees Celsius. Okay, let's see what else is given. The mass of the blood is given. Then the amount of energy is given. And then the original temperature is given, but I said we use that later. And then it says that the specific heat capacity of blood is the same as that of water, or approximately so. So I found one that lists at 3.78, and that compares with water, which is 4.136, I believe, or 4,186, depending on what kind of units we're in. So 4,186 compared to 3,780, and so which means pretty high, just as for water, which is by far the highest of most materials, most common materials. So they say, use the one that we have for water. So that one is given as 4,186, and so I'm gonna write down lowercase c, and then it's straightforward here. These variables here already suggest that I have to use the equation for specific heat. So Q equals C times M times delta T, and we're supposed to figure out delta T, and that N equals 2000 joules divided by 4,186 joules per kilogram in Celsius degrees. Yes, that's correct. And also divide by the 0.6 kilograms, and you come up with a temperature decrease in Celsius. And technically what we should do is, as the energy is being released, it's losing that amount of energy, so we should treat this one here as a negative 2000. So Q is given as 2000, negative Q 2000, so we come up with a negative temperature difference, and then we add to that the original one, the 37.0 Celsius degrees, and as we do that, we come up then with plus something, and that's going to be in Celsius degrees as well. And I can just tell you it's a little bit, let's see, it's a little bit less than 1 degree Celsius. And when you write this one in one significant figure, because that's what these numbers here suggest with the 2000 and the 0.6 kilograms, one significant figure, so it's going to be point something. As you subtract that, you're going to come up with 36 point something, and because you're subtracting that one significant figure here, as you're subtracting this in the front here stays. It had originally nothing to do with the calculation over here, and then as I said, you're going to come up with something right here. At this point, I may want to say something about the delta T, the difference in temperature, and being expressed in Celsius degrees versus kelvins. Notice also that the C is expressed in joules per kilograms and Celsius degrees, but it could also be expressed instead by divided by kelvins. And we had the same thing for the linear thermal expansion. It was the units were in 1 over Celsius degrees, but it could be also in 1 over kelvins. And the reason is that for temperature differences, which is Celsius degrees or kelvins, that we can use either one, because if you're writing 37 degrees Celsius going down to, let's say it is 36 degrees Celsius, that's a difference in 1 degree. But notice if you wrote this in kelvins, you would have 310 kelvins going down to 309 kelvins, and the reduction is just the same, 1 Kelvin. And that's why for temperature differences, Celsius degrees and kelvins are interchangeable. And I also put that in Blackboard kind of as a disclaimer onto where you're linking to these videos, saying that for temperature differences it doesn't matter if you're in kelvins or Celsius degrees as long as you're consistent. For absolute temperatures, which we will encounter in the next few chapters, that is important that we have to be in kelvins. But here for temperature differences, either way, Celsius degrees or kelvins is fine.